I want to tell you key equations of heat exchangers. So there are three key equations. All three you already know. So one is duty of heat exchanger. And by the way, this is section 11.3 in the book nobody likes, but anyway, if you want to go back, the book says so much more than I say, right? And the duty, remember I said, is the heat exchange between hot and cold fluid, right? And there are two ways of doing it. Calculate the heat exchange rate and all that stuff. Or you can see, okay, the hot fluid, how much temperature it lost. If I know how much temperature it lost, I know how much heat it lost. Or the cold fluid, how much temperature it gained, right? So that is an energy balance, which we did in the first week of class. So this would be all right, Q, watts, right? That's duty. Duty of the heat exchanger is mass flow times enthalpy lost. The enthalpy of the, if I put the H, I'm talking about the heat flow, the hot fluid. Enthalpy of the hot in the inlet minus enthalpy of the hot at the outlet. And this should be the same right? And so this is equation 11.6a, 11.7a in the book. You already know this. And this is super powerful. This accounts for phase transformation, phase changes, whatever you want. Now, let's say we're talking about a heat exchanger without phase change. Without phase change, we would have Q, the duty is, these are small c's. We're going to see that this is, those are the equations in the book, right? You know this. We did it. We did it in the first week of class. And an effort we've been making in this class is that we were paving the way for heat exchangers through the whole term, not just 1 week, the whole term, right? So these equations, and you're going to see that how easy to implement they are, because people typically say, oh, I need to cool oil that is coming at 100 degrees, and I need to cool it to 60 degrees. All right. So I would know the flow of oil. I would know the specific heat of oil because it comes from a table. They tell me the temperature at which it comes, the temperature at which they want to cool it. Right there, bam. You got the duty, yes. Can we assume the C is constant over? Yes, we're going to be assuming C is constant as we have been doing all along. Now, what about in industry, you do even less than this. In industry, you have just tables that say, what do you want, this? Okay. But so you guys are gonna be some serious engineers. So, but if you wanted to do a variable specific heat, you have the enthalpy here, and with this you can do whatever you want, right? So this is equation number 1. Equation number 2 is size of the heat exchanger. Or what people in industry call it, or at least in your design class, they call it the design equation. Isn't this like a super awesome name? Oh, what's the design equation for this heat exchanger? Well, let me write for you the design equation for heat exchangers. There you go. That's the design equation of heat exchangers. Now, yeah, my mind is blown, right? But these are all things you already know here, except one little, well, something you also know, but is here. Anybody remembers what this is called? Let's anybody remembers what U was? And it's not velocity. I give you that pointer. This is the overall, our good old friend, heat transfer coefficient. Remember when we talked about thermal resistance and we put them all together and we said, well, all together we have this thermal resistance? Well, there you go. And actually in industry they call it U, just as we have been doing. Now you know everything about it, right? This is what you put here. And of course, because in a heat exchanger you're going to have convection of one fluid plus the wall of the tubes plus convection of the other fluid plus fouling plus whatnot. All together, U, right? Okay, A. This is the heat exchange area of the heat exchanger. So in this equation, the whole point of this equation is solving for A, right? And this is called the design equation because it's going to tell me if I need this tiny heat exchanger or a monstrous heat exchanger, right? That's it, the whole point. So funny as it looks, like having this tiny equation, that is a very important one. Now, delta T, so this equation we had discussed before, but the delta T here comes with a trick. This is F okay, so what do I have here? Let's start with this delta T, right? Delta T is a change in temperature. When you saw internal flows, Yang went over this. If here I'm exchanging a lot of heat and here I'm exchanging little heat, what is the delta T? Is this other one? Is something in between, right? Of course, something in between. What something in between? So now, if we assume constant heat capacity, if we assume everything essentially constant, what we do this integral here, and what we come is that the heat exchange can be expressed with this equation when the delta T is a delta T log mean, right? That is delta T2 minus delta T1 over log of delta T2 over delta T1. Right? When you did internal flows, Ying derived this. She did this from scratch. And this comes from integrating this equation. Now, that is internal flows. That goes in the final. But from the point of view of heat exchangers, you just use it, right? And now if I flip 1 and 2, no problem. This becomes negative, and this other, they flip and become negative 2. So 1 and 2 don't matter at all. So the delta T for heat exchangers is the delta T log mean. There's one last trick. Remember I told you, if you have very complex heat exchanger, you just call it counterflow. That's why I put the CF here. This means counterflow. If you have very complex heat exchanger, you just say, I'm going to claim it's counterflow. And F does not stand for fudge factor, but it's what it is, right? F is a correction factor. Yeah, you had a question. Okay, so let me show you. Here, in this case, you have one shell, 2 passes. Very common heat exchanger. Very common heat exchanger. Now, as the flow goes this way, imagine this flow comes this way, the outside comes right to left. This is going right to left. So this part of the heat exchanger here is parallel flow, the one you don't like, right? But it's okay, that's the way it is. and then it bends and comes back as counterflow. So we have a heat exchanger that is kind of half and half, right? How do we go about that? And the way we go is, don't worry, you have these tables. And these tables, funny enough, they're in the online version of the book. They're not in the paper version of the book, right? So if you bought the book, you have to go and download this appendix. I don't remember the number of the appendix, but it's an appendix that has all these curves. But they're in the notes. So here is F, and here it says, depending on a ratio between these temperatures, right? You just have to plug and chug, like as we have done many times before. Depending on this relationship between temperatures, it will give you this F to put there in the correction factor. Now, 1 shell, 2 passes, 2 shells, 4 passes. Hey, unmixed, cross-flow, mixed, cross-flow. The real difficulty of the heat exchangers from the fundamental point of view is getting these curves, but the curves are there, right? So you can now calculate very complex heat exchangers. Everything we had done so far, you knew this, week 1. You also knew this. This is actually week 1 too, but this you knew from internal flows. The only thing that is new for heat exchangers is getting this correction factor that is specific for these different complex types of flows.